Driving in today, went by a barber shop. It was open. I was tempted. I was so tempted, but I didn't know what their protocol was. I was so upset. Look at this, out of control. Man, I need to get a haircut. Oh, look, all right, anyways, moving on. You don't need to know my problems. You don't need to know. Let's see. Oh, I got a Hawaiian shirt on today. It's nice out today. Nice out. Summer. On our list, I haven't covered everything. And I know some of you are list people, and you're going, you didn't cover that. How am I supposed to, how? Okay, I'm here for you. The two videos so far we've done on atomic history covered up through Dalton and then after Dalton to Chadwick in the 1930s. But there are a couple of laws that came in during that time that we need to go over. Laws happen every single time. They've never been shown to be anything different. It's an observation, happens over and over and over again, and here they are. The first one, you know. You do. I know you know. So it is LOCM, the Law of Conservation of Mass, or Law of Conservation of Matter. Same thing. And you know what it is. If I started out by saying, mass cannot, boom, you fill in the blank, you know it, cannot be created or destroyed. Okay, and most people know that have taken some kind of science course. This is a very commonly known law. Now, however, you might not know that there is an addendum to it. If you just say the mass cannot be, or matter cannot be created or destroyed, and stop, you haven't gotten the whole thing right. Okay? Because in 1945, and we all remember where we were in July of 45, okay? I remember it well, sunny day. Out in Los Alamos, New Mexico, there was the first detonation of an atomic weapon. Yeah, that nuclear reaction had an effect on this law. The addendum is as follows. Mass cannot be created or destroyed, comma, in ordinary chemical reactions. Of course, in chemistry, we do ordinary chemical reactions. We don't do nuclear reactions. But a nuclear reaction, you can destroy that mass. And when you do, you get a butt ton, very scientific word, a butt ton of energy out of it, hence the big nuclear explosion. So that law needed an addendum. Okay, that's law number one. Actually developed in the early 1700s by Lavoisier, French chemist. And he actually was in France during the whole, revolution thing, and it didn't end well for him at all. No, not at all. Okay, moving on, late 1700s, Proust, another French chemist, came up with the next law that we need to go over, law of definite composition or law of definite proportions. I wrote it down as proportions. Either way, same thing. Law of definite composition and proportions. Okay, what's this one saying? This one's not too bad either. It's relatively straightforward. Let's take water. H2O. This is the law of definite proportions or composition. H2O is always H2O no matter where you get it. If you get water from, we're talking about high quality made in America water from Lake Ontario or Lake Winnipesaukee or from the Ohio River, it's always going to be H2O. It makes sense, right? I mean, you go, well, duh, it's water. Yeah, I know, but in the late 1700s, this law was not such a duh. Okay, people are just discovering this stuff, that water is always water. It makes sense, but now we know that water is always water. But there's actually a little bit more to it than just saying water is always water. That's kind of really simplifying it. Like again, if I get water from a glacier from the French Alps, it will always be H2O. It has a definite composition to it. But there was a little bit more to it to be fair. Okay, be fair. It has to do with a mass proportion or a mass ratio. So the mass ratio of H2O, no matter where you get it, as long as pure 100% quality H2O, is always going to have a mass ratio of, hydrogen is a mass of 1, round them off. Don't use the 1.00797 on the periodic table. It'll go nuts, just round them off. 1 times 2 is 2. Hydrogen is 16. We round that off to a whole number 16. The mass ratio is going to be 16 to 2. When I do ratios, rataio, it's an Italian word. Look it up. the 16 to 2, 16 goes on top because it's bigger. Most people put their mass ratios so the larger number's on top. Something to 1, something to 1, something to 1. You can do it the other way around. It's not wrong, but people are going to laugh at you. Yes, they are going to laugh at you, and you don't want people laughing at you. So, bigger number on top, smaller on the bottom. We get an 8 to 1 ratio. The mass ratio for water is always 8 to 1 in favor of the oxygen over the hydrogen. Okay, so if these were in grams, if this was 2 grams, 16 grams, it would be 8 grams to 1 gram. For every 8 grams of oxygen, you have 1 gram of hydrogen. That's a mass ratio. That's a definite composition always for water. And of course, if it's not water, it'd be a different ratio. So if you had CH4, let's say you have some methane, and that would be 4, because there's 4 ones, and 12. That mass ratio is going to be 3 to 1. So, yeah, methane's always methane, it's always a CH4, that's what methane is, and it always has this same definite, see, there it is, the word definite composition of a mass ratio of 3 parts carbon to 1 part hydrogen. Okay, so that's definite composition. Always the same, no matter where you find it. And of course, if it's always the same, it'll have that consistent mass ratio. All right, last one is the law of multiple proportions. Now we'll give you the simplified version, and we'll do the, okay, let's be fair version. This is what it really says. Simplified version is that you can have multiple, hence multiple proportions, multiple combinations of 2 elements, and it doesn't have to be 2 elements, but usually is 2 elements. Okay, they can form multiple compounds. For example, now we have to do this so one of the elements remains the same. So we're always comparing something to one when it comes to ratios or proportions, multiple proportions. So if we keep our carbon as just one of them, we can add multiple combinations of the oxygen, CO, CO2. We can do this with nitrogen compounds, carbon compounds. We can go nitrogen. Keep the nitrogen as 1, nitrogen O, nitrogen O2, nitrogen dioxide, nitrogen trioxide. Okay. So what this law is saying is, okay, 2 things. Well, 1, we can have multiple combinations of elements to make multiple compounds with the same elements. Okay, that's one. That's the really dumbed down version. But you people want the mass part of it. Yes, you do. Yes, you do. If we take the carbon and the oxygen and look at their masses, 12 and 16, in carbon monoxide. If we take the carbon, 12, and the oxygen here, there's 2 of them, so that's 32. And let's get a ratio for them. Remember ratio, big number on top, small number on the bottom. 16 divided by 12. 32 divided by 12. Okay. 16 divided by 12. Anybody? Boop, 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 boop. You come out with 1.12 evil. 1.12 evil. Think about it. Think about it. 1/2 evil. 333. 1.333. Get it now? 1/2 evil. 333 half of 6. This one here comes out to be 2 point evil. 2.666. Okay, we just looked at the mass ratios. Here are the mass ratios of the elements in the compound. Okay, we always take the larger one, put it on top, divide it by the smaller one, and we get these numbers. Well, so what? I get those numbers. They're not the same. No, they're not. They're not, but check this out. This is what the law of multiple proportions really says. It says, yeah, you can get different combinations of the same element making different compounds, and when you compare the mass ratios of them, now let's compare the mass ratios. Here's our mass ratio, 1.333 and 2.666. You compare those, this one is exactly twice the value of that one. Ooh. So whenever we look at the mass ratios, we get a whole number. Now if I'm going to take this one and divide it by this one. Okay, I'll do it. Equals 2. Okay, you get a nice round whole number ratio when comparing the mass ratios of multiple compounds with the same elements. Now, I know that sounds very more complicated. It is. It's probably the most complicated of the three, but it's really not that bad. What it says is you have, again, compounds, two elements, can make multiple combinations. If you compare the mass ratios of those different combinations, then they always come out to be a nice whole round number. Okay? That's multiple proportions. And that was a John Dalton one. He did that one in 1804, if I remember my history right, and I usually do. Love history. Love it. All right, I think that wraps up our history until we get to the periodic table. When we get to the periodic table history, that will be in a week or two from now, a little while from now. No, actually, it'll be longer than that. But we'll eventually get back to more history. But for now, that makes like a gift and wraps up history. Woohoo!